Hello. What we have here is a short lesson on relative motion, and what I have set up here is a situation with two cars that are moving towards each other, and there's car A, which is moving at 10 meters per second to the right, and car B, which is moving at 8 meters per second to the left. But one of the things that we've never really mentioned until now is the fact that all motion is relative, and what that means is it's given with respect to some observer, and we've never been really clear about who the observer is, but we usually just imply that it's some person or object at rest on the ground. So I've included an observer here, and that's person labeled C. And C is a person standing at rest on the ground, so it's not moving relative to the ground. So the velocity that you have here is what C sees A doing, and the velocity that you have here is what C sees B doing. And the way that we write relative velocities is the velocity of A with respect to B. So what this term here means is A as seen by B. So 10 meters per second here is really the velocity of A, this object, as seen by C, or with respect to C. And then the negative 8 meters per second is the velocity of car B with respect to C as well, also what this person sees. Now there's other perspectives to view here. We could ask, what does A actually see B doing? And if you've ridden in a car or a train and you look outside occasionally, your brain can actually convince you that you maybe are not moving at all or moving backwards depending on the thing that you're looking at. If you look out at your car out of a car window and see something passing you, if you weren't really paying attention to the surroundings, you could think that maybe you were just moving backwards while the other car was stationary. So A actually sees B moving towards it rather fast. It doesn't see the car moving at 8 meters per second towards it. It's a combination of these velocities. And the way that we can mathematically figure this out is by using this relationship, which adds together relative velocities. And the way you can kind of remember this is that the velocity of A relative to B is going to be equal to A relative to C plus C relative to B. It's the outer terms that end up over here, and the inner terms just kind of go away. That's a way that you can kind of memorize this equation, I suppose. If you just think about it, I suppose, if you're looking at car B while you're in car A, what you'll end up seeing happening is it'll look like B is approaching you at 18 meters per second. A is going to see B moving in the negative direction to the left at 18 meters per second. In the same way that if you're traveling at 50 miles per hour and the traffic traveling the opposite way is moving 50 miles per hour, it looks like it's moving at 100 miles per hour as you pass by it. But we could show this mathematically too. Before we do that, another note is that the following is true. The velocity of A relative to C, which in this case is 10 meters per second, is equal to negative the velocity of C relative to A. In other words, when you flip these indices around, you're just adding a negative sign. So while A appears to be moving to the right at 10 meters per second, according to observer C, if you're in car A and you're looking at observer C, they appear to be moving towards you at the same speed that you're traveling because C is at rest relative to the ground. So if you're a passenger in this car, you see person C, moving to the left towards you at 10 meters per second. So that's where this comes from. So if I want to find the velocity of A as seen by B, so let's say that we want to find out, and this means that B is observing A. So what is B see A doing? B should see A moving to the right at 18 meters per second. And we could show that mathematically. First we have to find the velocity of A with respect to C, which we have here. It's 10 meters per second. We have to add to that the velocity of C relative to B. We actually have B relative to C, but because we can just switch the indices and then add a minus sign, the velocity of c relative to b will be the opposite of -8, which is +8. And we do get our positive 18 meters per second. So what B sees A doing is moving to the right at 18 meters per second. And if we want to try to find the velocity of B relative to A, we could just do this flipped thing again, where if A relative to B is +18, then B relative to A must be -18 meters per second. And what we said originally was just that car A would see B moving towards it, which would be the negative direction, at -18 meters per second. And this whole process also works in 3 dimensions. And one way that you could try to visualize that is answering the question, what is the velocity of this boat relative to the land? Now, the story goes something like this. There's a river current that can be represented with this velocity vector, and I've called this the velocity of the water with respect to the land. So here W is water, L is land, and B is boat. So the velocity of the water with respect to the land is kind of like how the water is moving down the river. It's if you put a leaf into the water and then watched it go by as you were standing on the land, what velocity would that leaf have? It's something like that. The velocity of the boat with respect to the water, that's how the boat is moving if you were that leaf in the water looking at the boat. It's not the same as the velocity of the boat with respect to the land. Now, if you set off on this boat and you wanted to go across the river to this dock, and you point the boat directly to the dock, you might think that you would move straight towards it across the river and get to the dock. But there's the river current, and the river current is going to push the boat downstream. So even if you point the boat straight across, you're probably going to go off in a diagonal direction. And we can show that. We could show that with the relative velocities. If I want to find this velocity, using the idea that I could find the velocity of one thing relative to the other using this pattern, I need to add together the velocity of B relative to the third thing that isn't the boat or the land, and that would be the river, or the water in this case. This is still land, but this is water. And then I need water as the first term here, and the last term being the land. So the velocity of the boat relative to the water plus the velocity of the water relative to the land should tell me the velocity of the boat relative to the land, and it'll show me where the boat lands along the shore. So we have these vectors. The boat relative to the water, that's this vector. Now it says to add this vector, the boat relative to the water relative to the land. That's this vector right here. And the way that you add vectors, as we've seen before, is the tip-to-tail method. So if I take the boat relative to the water, add to it the water relative to the land, the resulting vector looks like this. And that is the velocity of the boat relative to the land. And it does what we expected. It points off to the right as well as upwards, meaning that the boat is actually going to travel that path and land somewhere over here. So if you point the boat directly across the river, you're actually going to drift. If you wanted to make it to the other end, straight across, you would have to point the boat's velocity relative to the water into the current this way, and that way you could actually go straight across, depending on the velocity of the river as well. So that's just a little introduction on how you could use these relative velocity equations to solve problems.